This is a multi-part series to develop drone airfoils with leading edge and trailing edge flaps. Part one is how to use Xfoil to analyze the airfoils. I wrote this presentation for free or pro bono to help people design better fixed-wing drones. I'll briefly summarize the slides, but to get the full understanding, you'll need to pause the video and study each slide in detail. Purpose of the report, one is to allow the first-time users of Xfoil to quickly use the program and analyze some airfoils with flaps. And second is to determine the optimal flap configuration for an RG-15 airfoil. Here's some definitions. The design goals, the first goal is to maximize the range by using a low drag coefficient wing. The low drag minimizes power consumption, thus improving the range. The other goal is to reduce the takeoff and landing speeds with a high lift coefficient. We accomplish this by selecting a low drag coefficient wing and changing the shape of it. So here's the initial wing, and here's changing the shape of it by using a leading edge flap and a trailing edge flap. And here's some examples of some analysis done. Here we have a wing with no flaps, and here's the angle of attack, the coefficient of lift, coefficient of drag, and the coefficient of lift, the most we can get was 1.13. Here's the same wing, but with leading edge and trailing edge flaps, and the coefficient of lift went up to 1.95. The inputs for this analysis were the RG-15 airfoil geometry, the Reynolds number, and then the pivot point distance from the trailing edge flap to the front of the wing, the angle of the flap, the pivot point distance from the leading edge flap to the front of the wing, the angle of the leading edge flap, and then the angle of attack. And the outputs were the lift coefficient, the drag coefficient, and the moment coefficient. So here's the actual script that was used, and the flap geometry was defined by these lines in yellow. So as on the previous page, there's a value DLE, ALE, DTT, and ATE. And again, refer back to this previous page for the definition of those. Line 20 aligns the airfoil correctly in the case where the leading edge flap is used. You enter the negative value of the amount of leading edge flap deflection here. And copies of the script are in the shared Google Drive at the end of this presentation. Here are the instructions to set up the batch files. Here's what the Xfoil output looks like. And here's how to transfer the Xfoil output into an Excel format. Here's the Xfoil output in an Excel format. This is a plot of the lift coefficient and the drag coefficient versus the angle of attack. As the angle of attack increases, the lift starts to increase until flow separation or stall starts to occur, and then the lift drops off. Xfoil is only accurate in the region before the flow separation or the stall occurs. Do not use any of the values after flow separation or stall has occurred. Here's a summary of 25 Xfoil runs that were made. And the airfoil that had the leading edge and the plain flap or the trailing edge flap had the maximum coefficient of lift of 1.96. This airfoil also had the largest lift to drag ratio of 36.3. Xfoil predicted a coefficient of lift that was about 8% higher than actual wind tunnel tests. So a comparison was made between the Xfoil predicted lift coefficient and the actual wind tunnel lift coefficients that were measured. And this was done for an RG-15 airfoil with flaps and also done with another airfoil, the W1015, and the same thing for the NACA0009. During your setup of the Xfoil, the best value for the PPAR was found to have it set at n equals 200. And the best value for NSEEK, the angle of attack increment, was a zero point 0.2 degree angle of attack increment. And the next three slides, give an explanation why. So this is a graph of the same airfoil flight condition, and what was varied is different values of the uh, angle of attack increment and the N value. And ideally, these would all be one single graph, but you see there is some variation due to changing these values. Um, and in the worst case, the uh, the lift coefficient varied from 1.9 to 2.0, or about 5%. Comments on the Xfoil program. Xfoil was very fast to run on the computer. Typically, an analysis is done in less than a minute, and the program is also free. Also remember that Xfoil will tend to predict a coefficient of lift that's about 8% higher than it actually is. Um, and when you do your setup on Xflows for the PPAR, use a value of N as 200, and the ASEQ, use an increment of zero point 0.2 degrees. The other thing at Xflow will do is sometimes it will skip, it won't converge, and it will skip an angle of attack number. So here we've requested it to go from 0 to 20-degree angle of attack and calculate the coefficient of lift and drag and moment. And it skipped the 10-degree value and the 19 and the 20. So just realize that it will do this, and your Excel spreadsheet will not have all the data in it. Here's a design I came up with to evaluate the performance of these flaps. We've got a single servo motor that has linkages that activates both the leading edge flap and the trailing edge flap. And so here we are in the cruise mode. Here we are in a takeoff mode where we've got a little bit of a deflection here. And here we are in a landing mode where we've got basically we have about twice as much deflection on the trailing edge flap as the leading edge flap. And here's a partially built aircraft that I'll be using to test and verify some of the airfoil results. It's a modified electric streak. So I have files that I'm willing to share on Google Drive. You can use this, use your cell phone to scan this barcode to get them, or you can just type in this into the Google Drive link to get access to those. And here's a description of the files that are there. Here are the file names. Here's a description of what they are. For the instance where I actually put in the Xfoil script, I give a description of what airfoil it is, and then the flap geometry and the Reynolds numbers, and just comments, flaps, plane flaps, leading edge, and plane flap. And here's some additional references that may be useful. And a little bit about myself. My day job is to design servo-controlled mechanisms and fluidic systems, and I do this aircraft design, as a hobby. So good luck with your design, and hope you enjoyed this presentation. Thanks.